Welcome. In this lecture, we are going to talk about voltage based digital pulse skip modulation and top down design method. So, here we will talk about digital pulse skip modulation in discontinuous conduction mode, and we have discussed in lecture number 50 that this pulse skip modulation technique comes into picture when the converter operate in light load, particularly in discontinuous conduction mode, where we want to save losses, switching losses, and by that way we are trying to improve the light load efficiency. And here we will discuss about top down design methodology of digital pulse skipping modulation. So, if we recall lecture number 50, we have discussed that classical analog pulse skip control, where we are simply considering V0 and Vref, and this will be compared at the edge of the switching clock, and if V0 is smaller than Vref, then this Q PSM will be 1, and it will simply pass this PWM, and the effective switching clock will be nothing but the PWM clock, and the waveform is shown here. So, this part we have discussed in lecture 50. Now, if we consider the digital, here we are only replacing digital. So, remember, we may consider, suppose if we are talking about multi-mode control that we will discuss, we may keep even this part, we may or may not need any ADC as well, or we may continue, because if we are talking about multi-mode, that means in under high load or continuous conduction mode, we will be using either digital current mode control or digital voltage mode control, where the ADC is there. Now, in this case, we can use this ADC because we have to keep track of voltage deviation and all, and that ADC information can be used for this pulse skipping operation. And here we are talking about very rudimentary, like a basic pulse skipping, where we have a fixed duty ratio clock, and only thing the Q will either take the PWM clock or it will be 0 when it is skipped, depending upon the status of this output voltage and reference voltage. And these are sampled at the every switching edge of the switching clock, and which is nothing but the sampling clock. We are taking the same as the switching clock, and this we have discussed in lecture 50. We have also discussed that we can do, because earlier we have used a fixed duty ratio, and we will discuss in the subsequent lecture. Fixed duty ratio will have a problem for varying input voltage, because if you keep the duty ratio same and if suddenly the input voltage increases, so you may actually have large current ripple, and that may increase your voltage ripple also. Okay. Similarly, if the input voltage drops, we will discuss, it may so happen there may not be any pulse skipping operation even under light load. So, the selection of duty ratio is important, but in digital circuit you may update the duty ratio based on your switching frequency consideration, right? Because if you find that your number of skip cycles are reduced and more number of charge cycles are going, then you should understand that there is a time to increase the duty ratio. So, duty ratio adaptation may be possible. Alternative way, we can do by a current based PSM. How does it work? Instead of giving a fixed duty ratio, the duty ratio can be generated by comparing with the current. But all IC, because you may or may not have this current mode implementation, here we need to consider the analog current loop. Okay. So, that means the duty ratio will be generated by comparing the current reference and the inductor current, and that will give you the duty ratio during the PWM operation. But it may so happen that the problem in this technique, that if you operate under very light load condition, that this current comparator, if you turn on and off, because we have to disable also during skip cycle, we have to disable this operation. Otherwise, if you continuously operate this comparator for every cycle, even though you do not need a charge cycle, then like in this case, if you see that as if this operation is disabled, but it depends on unless if you disable this comparator. Otherwise, every time this signal will be there, actually I would say this waveform, you will always find this waveform will be there, but you may not consider this waveform during the skip cycle, because we found these two cycle the output voltage is higher than the reference voltage. So, the basic logic of the skipping cycle of the selection of whether charge cycle. So, what do we call charge cycle? When the PWM signal is passed, that is called charge cycle. When your actual duty ratio gate signal will be turned on and off, but when it skip, that means there is no, if the output voltage is above the reference voltage, the cycle is skip, that is called skip cycle. So, you will see for these two cycle, for let us say this edge is 1, this edge is 2, this edge is 3, this edge is 4. So, for second and third edge, the output voltage is above reference voltage, that is why we need to skip the cycle, and during this time the Q will not see the PWM signal, it will be disabled. But since we are not using a separate disabling clock, the current comparator will continue to operate. So, that means every cycle the current comparator will operate. So, this may, because if your number of charge cycle is more, so unnecessarily you are burning power by this current comparator, and that too under very light load condition, and that may actually increase your power loss. So, you have to be careful. The one way you can disable this block during this operation, that means this operation you can disable, that means I would say you can disable the comparator, this comparator can be disabled, by that way you can save power. Again you have to enable the comparator when there is a charge cycle, and this enabling and disabling of the comparator may be faster compared to the switching frequency. So, we have to keep that thing in mind. Now, if we go to, we have discussed the basic feature of this analog current base, but the good thing about this technique, since it is there is a current reference, so you will not actually, you will always protect the circuit, that is one aspect for protection point of view. The second part is that you are always giving a current limit. So, that means if your input voltage is high, so that means let us consider this scenario. So, you have a current reference. So, now if you see this on time T on, and this is the slope of the current, and this is I ref. So, what is your T on? T on by T is, or basically instead of T on you can say it is a duty ratio, you can say it is a duty ratio, that will be much easier, D into T. Then your D into T into M1 is equal to I ref. So, your D will be I ref divided by M1 T, and what is M1 for a buck converter? It will be I ref into, what is M1? It is, that means it will be L by T into 1 by V in minus V0. That means whenever there is a increase in the input voltage, then naturally, since that means what is the expression of duty ratio we will found? If it is 1 by V in minus V0 into I ref into L by T. That means if L is T, L, T are fixed, I ref is fixed. So, duty ratio is basically inversely proportional to 1 by V in. That means if V in increases, duty ratio is decreasing. If V in decreases, duty ratio is increasing. So, by that way we can actually make sure the pulse skipping is happening, and also we can ensure that current limit is not crossed. But again we have to consider this practical part into consideration. And we have discussed in lecture 50 the mixed signal, where we can consider the voltage digital, because if as if it is a part of mixed signal current mode control, where in continuous conduction it is typically the peak current mode control, and the peak current reference will be coming from where? It will be coming from your outer loop of the PI controller, and there we may not be providing any pulse skipping, because under high load we do not want pulse skipping, and then we can disable this. Otherwise we can use this digital voltage loop and continue to operate in peak current mode operation, but we have to make sure that we need to ensure enabling and disabling of this comparator, otherwise we will be burning lot of power during light load condition. So, the implementation of this block, what we have to implement, this is our practical circuit, this is ADC and you have to generate gate signal. So, the ADC data to this will be in your digital. So, that means it will be your part of FPGA that we are going to implement. So, we are taking data from ADC and that data we are calling ADC data, and we have discussed in the previous lecture in digital voltage mode and digital current mode control. So, ADC data is coming and we are only taking about digital pulse skipping, no current base, it is just a fixed duty ratio base. So, the duty ratio command we have to provide for the PSM block, but this command can be adaptive. That means, this command will give you the duty ratio which can be varied based on how many number of skip cycles. So, if there are too many skip cycle, then you have to consider the current is high, we can reduce if the input voltage increases, but if there are less number of skip cycle, you can always increase this duty ratio to anticipate. So, we need to effectively design this Verilog module, and this will be our FPGA, will be sitting inside the FPGA digital, which will generate the PWM high low, and we are not making any load transient. So, this can be set to 0, that means, it will always consider the high load resistance, which means under light load condition. But we can make a reference transient, anything transient is possible. In fact, when you go to multi-mode, we can use this load and it will switch between PSM and PWM, that case also will be considered in the subsequent lecture. So, we have to make this module, that means, this is my overall module and we have to do a top down. So, the main module will be digital pulse skipping, and this module require a clock generator to generate the clock for the ADC, and this will take the input clock as the F clock, and which is like for our case is 100 megahertz clock. The ADC clock, it is up to you. For light load operation you can reduce the ADC clock, but we have considered for high load around 25 megahertz clock for the ADC, because to reduce the effect of sampling delay, otherwise your pipeline ADC has 6 cycle delay. If you use slower rate for the ADC sampling, the effective delay will increase and that will cause stability issue, and we will be discussing about the sampling delay aspect in the subsequent lecture. We also need a PSM logic which will be inside this block, and finally, this PSM logic will consist of a PWM generator and a PSM logic, because we have discussed the actual gate signal will be an AND of, you can say, PSM and Q PWM. So, when the PSM is low 0, then Q will be simply 0 and it is called skip cycle. When this is high, it will take the PWM clock. So, we will be discussing Verilog program in the next lecture. So, in summary, we have discussed digital pulse skipping modulation in discontinuous conduction mode. Then we have discussed top down design methodology of digital pulse skipping modulation, and in the next lecture we are going to show the Verilog coding, which is simple. We already know the other Verilog codes, and then we will also show some experimental case study. That is it for today. Thank you very much.